Hi, in this video I'm going to go over an example of a circuit of, I guess, what you might call medium complexity. It has a battery and 4 resistors, and they're connected up as shown in this diagram. The principles that we're going to use you can apply to circuits with, 5 resistors, 10 resistors, 100 resistors, 1,000,000 resistors, at least in principle, that you'd probably die before you're finished. Alright, so we want to solve this circuit. What does this mean? It means we want to find the current through every single one of the resistors and also through the battery, and we want to find the potential difference across any one of those resistors. Now, the battery gives us 12 volts, so that means it's going to be 12 volts from here, say, all the way around, right? So you can already see, say, that the voltage across this one, or potential difference across this one, plus potential difference across this one, for example, should add up to 12, right, from Kirchhoff rules. But how much goes here? How much goes here? Difficult question. Let's figure it out. Now, one way to solve such a circuit would be to systematically apply the Kirchhoff rules, junction law, and the loop laws, and Ohm's law for each resistor, and then solve for all the unknown variables. That will work. It will get you there. In this example, though, I'm going to do it by the other method, which is to simplify the circuit by working out equivalent resistances. So we're going to step by step simplify the circuit until we've got a circuit with only a single resistor, and then we're going to work backwards and essentially unravel our simplification and step by step work out all the values. So the first thing you want to do when you have a resistor like this, you want to label your resistors if it hasn't been done for you already. Sometimes it can be useful to just label them by their resistance. So I'd call this the resistor 4. But I run into problems in an example like this one where there are multiple resistors with the same resistance. Right. So I'm just going to label them. Because I'm not very imaginative, I'm going to call them A, B, C, and D. Okay. Now, if I did this live, step by step, you'd probably still be here in, I don't know, 40 minutes time. So I actually did the work for this one in advance, so we can just look at what the solution path looks like, and you can use this as a kind of template to solve other resistor circuit problems. So here's the solution, and I'm going to walk you through it. This is the complete solution to the circuit on a single page. It doesn't quite fit on my camera, right? But we're going to get there. So you're confused right now, that's okay. It's a big sheet of paper. We're going to start here. And step by step, we're going to simplify the circuit. And then we're going to start calculating currents and voltages across individual resistors. And step by step, unravel our circuit until we get back to the original circuit. Right. So a circuit that you want to analyze is this one here. And that's the one I've copied right there. So let's start. You look at this and you try to identify which resistors are in parallel, which are in series. You will be able to start somewhere. If it's a circuit with just one battery, there are gonna be some resistors which are in series or in parallel. Right? No matter how complicated the circuit is. If you have a hard time finding them, just use the method where you color each sort of segment of wire in one color in a different segment, separated by the resistors of the battery, a different color, and use the method of looking, well, if I go from red to green here, is there another red to green somewhere, then those two would be in parallel. If you find some in series, it's usually easier to spot, because it just means you need to find a wire that doesn't have any junctions in it and just connects to resistors. So in this one, that's where we start. I look at this side here and I see, hey, C and D, they're in series, because any electron that comes through here will have to go through the other one as well, right? If you go through C, you've got to go through D. So those two are in series. Okay, so that's going to be our first simplification. We calculate the equivalent resistance of those two. Now, those are both 3 ohms. 3 plus 3 is 6, right? Resistors in series, add the resistances. So now we have our simplified circuit here. We've got the original resistor here. We've got B is still B, but C and D have been combined into one. I'm now going to call this X. Alright, that shows X rather than say E to sort of reserve the beginning of the alphabet for the actual resistors that are there, and then the end of the alphabet for the ones that are equivalent resistors. So now I've got this set up here, and it's still I can't solve it, but now I can see, hey, those two, they are in parallel, right? If I start here, I can go through one or the other, and we're going to end up again in the same spot. Or if I color this segment of wire up here green, this bottom one red, then they both would take us from green to red, from green to red, so I know they're in parallel. Okay, that means I can combine those. Notice that this one and this one, they're not in series, because there's a junction in between. That means if you're an electron going through this one, you don't necessarily have to go through this one. Similarly, this one and this one, they're not in series, because there's a junction. So I have to eliminate the junction first. And I notice, hey, those two, they're in parallel. Okay, parallel, it's a little bit more complicated, but you know the rule. The 1 over the first resistance plus 1 over the second resistance is equal to 1 over the third resistance. A third plus a sixth is a half. Okay, so that means the combined resistance of those two is 2. And the equivalent resistance of those two in parallel is a single 2 ohm resistor. Of course, 2 is smaller than 3 and 6 because it's easier to go for the electrons to essentially have both routes open than just either of single one. It's always what you expect when you've got resistors in parallel, that the combined resistance is less than any individual resistance. Okay, let's make the simplification. Notice I've tried to color code it so the green box becomes this green resistor here. So the combined resistance here is 2 ohms. Okay, now this already looks a lot simpler, and I can see straightforwardly, hey, those two, they're now in series. So I can just add those. 4 plus 2 is 6. And I've now reduced my circuit to a single one with just one resistor here. Okay, that one we know how to analyze. If it's 12 volts across the battery, it's 12 volts difference across the resistor. So now we come to the calculation part, right? We simplified our circuit all the way down to the simplest possible resistor circuit you can think of. So now we're here. So now I can calculate the current, right? I know the voltage across this one because it's just the battery. 12 volts. Current is voltage, potential difference over resistance. So it's going to be 12 over 6. That's 2 amps. That's, of course, Ohm's law. And we're going to use Ohm's law over and over and over now, right? But I only wrote it down to one time here. Okay. So now we know the current through this one. All right. So now we're going to go back one step, right? We go back from here to here. So this is the circuit drawn again. So now those two, right, are in series. So what's the same is the current. Any electron that goes to this one has to go to this one. So the same current is going to go to this one as to this one. Okay, so that means the current through here, call it IA, because this is resistor A, and IY, resistor Y. In both cases, it's equal to the total current, the current, through the battery, if you like, because again, there's just no junctions in this one. Okay, so those are the same. We don't know the voltage across each, right? We know they have to add up to 12, but we don't know the individual ones. Well, we can use Ohm's law. So this one here is going to be I times R. We know I, we know R. Times R, 2 amps times 4 ohms, 8 volts. So 8 volts across this one. And then for this one here, we've got the same current, because those two are in series. 2 amps, 2 ohms, 2 times 2 is 4. 4 volts. Let's double check that this makes sense. 8 plus 4 is indeed 12, which is what Kirchhoff's loop law to this applied to this circuit, confirms. Okay, so now it gets a little bit messy. If you look very carefully what's going on here, what are we doing? Well, we're going from this one, right? This one was our equivalent resistor. We're going to split this into the two parallel ones. So we're going backwards, right? That's what I've done here. Taking this one and split it into those two. So in this case, because those two are in parallel, what's the same is the potential difference, right? The difference between this chunk of wire and this chunk of wire. Doesn't matter which way you go. If you walk down a mountain, you start here, you end up here. Do you take this path? Do you take this path? Well, you're going to be going down the same amount of height. So into parallel ones, the voltage difference, potential difference is going to be the same. So for the X resistor here, remember that's what we called this one there, X resistor here, potential difference across this is the same as the potential difference across this one here, right? Because this one here is kind of a combination of those two, but they're in parallel. So I don't know what the current is, right? The current through this one here, we worked out it was 2 amps, but how does it get split up? Is it equal? 1 amp, 1 amp, or is it, 1.9 amps and 0.1 amps? Who knows, right? Let's figure it out. The potential differences are the same. We're looking at this one right now. Notice the color coding. The potential difference here is 4 volts because that was the potential difference across this one. We know the resistance of this resistor here, so we can work out the current. Delta V over R, 4 volts over 6 ohms is 2/3 of an amp. Let's apply the same method here. Potential difference is going to be 4 volts, the same as this one here. Resistance is 3 ohms, so 4, where are we? 4 volts over 3 ohms is 4/3 of an amp. Let's check that this makes sense. 2/3 amps plus 4/3 amps makes 2 amps, which is what the Kirchhoff junction law would tell us about this point, right? 2 amps come in, 2/3 this way, 4/3 this way. Yeah, that adds up to 2. Current is conserved. Now we're not done yet because the resistor X isn't really there. It's a combination of C and D, right? Those two here. So let's split this one up now into C and D. Right? So we're exactly tracing those simplifying steps backwards now, in exactly the reverse order. So C and D, they're 2 3 ohm resistors, that's what we know. And because though they are in series, that means we don't know how the voltage difference gets split up. We know it's 4 volts in total from here to here, but we don't know, is it 2 and 2? Is it 3 and 1? Is it 1 and 3? We don't know. We can probably make an informed guess, but that's beside the point, right? We want to have a foolproof method. So we don't know what this is, we don't know what this is. But what we do know is that the current is the same. And the current through C and the current through D is the same, and it's the same as the current through X. Because X is the single resistor here, is the combination of those two. So the current through X is the current through the right branch of the circuit. This is the right branch of the circuit. Let's start with the C resistor. Well, the current is the same as X. We know what it is, 2/3 amps. So I'm just going to multiply this by the resistance. V, delta V is IR. Gives me 2/3 amps times 3 ohms, so 2 volts across this one. The calculation for the red one is exactly the same because the same current and the same resistance. So I get 2 volts here. 2 volts plus 2 volts is 4 volts. That checks out because that was the voltage across this one here. And we know the voltage across this one here was 8 volts. We worked it out right back here. So indeed 8 plus 4 is 12. And 8 plus, where is it? 4 going the other way is also 12. Okay, it all checks out. So now we know the current through each resistor and the voltage across each resistor. If you want to work out the power output, of course, as long as you know the resistance and either current or voltage, means you know the power output as well. It doesn't really factor into the sort of step-by-step calculation, but as long as you figure out the current or voltage through any one resistor, now you can figure out the power output of that resistor. So I hope that helped. I'm going to put just this sheet of paper up as well next to the link to the video, so that you can just look at it, and when you're faced with a different circuit, with different arrangement of resistors, you can apply the same kind of method. It gets a bit lengthy, but it's very mechanical, right? You can't go wrong as long as you keep track. I find the color coding helpful because it does get messy, but notice no single calculation is very difficult at all. So hopefully that was helpful. Have fun solving your resistor circuit.